And chapter 3, I might have already talked about this, not sure. But in chapter 3, we are working with systems of linear equations and inequalities. So I'm going to keep bringing that up as we go through the chapter because the first half and the second half might almost seem like they're two different units. The first half, even today, we review what you learned about systems in Algebra 1, and then we build off of that, so we even get into systems of 3 equations that have 3 variables that you didn't see in Algebra 1, but we can use similar methods. And then after the quiz, the second half of the chapter, we actually learn about matrices, which is the plural of matrix. So that might be brand new to most of you working with matrices. And after you learn how to work with them, the reason they're still in the same unit is you can use matrices to solve a system of equations. So it's all tied together with systems, even though the first half and the second half might, at the beginning of the second half, might seem completely unrelated. It does all tie in with systems. So today what we're talking about is reviewing just what a system of equations is, and then the graphical methods for how to solve it. So students have already brought up in my other 2 classes, well, couldn't we solve it this way? There are also 2 algebraic methods. So both today and tomorrow we're covering the methods you would have already seen in Algebra 1. We're just reviewing those. Although I do believe using a table, this one you might not be as familiar with, but I do want you to see the method so that you understand how to use it. So ultimately you want to be able to solve a linear system of equations graphically, and that could be just using a table or actually graphing it. And system of equations is defined to be 2 or more equations with the same variables. Usually your variables are x and y. They don't have to be. And then to solve a system of equations with 2 variables, specifically you're finding the ordered pair that satisfies all of the equations. So your answer is an ordered pair. So your answers should be written as ordered pairs when you're solving a system. So we are going to look at the method of using a table, and I have the steps written in that box for you. You first want to write each equation in slope-intercept form. And what is slope-intercept form again? So solve each equation for y, substitute different values in for x in step 2 here, and solve for the corresponding y values. And because you're trying to find the ordered pair that satisfies all of the equations, you're looking for the x value that you substitute in where then your 2 y values are the same. And then you're going to write your answer as an ordered pair. So it's finding that ordered pair just by looking at a table, not by actually putting it on a graph. And I did give a hint it might be easiest if the first x values you substitute in are 0 and then 1, since those are typically the easiest values to substitute in. So if we look at example 1, we're going to solve this system by using a table. So make sure, because I had this question as well, looking at the directions, if the directions specify a method for you to use that method, because I'm still going to assess you. I want to see that you know how to use each method. Ultimately, then, if I just said solve the system, you could use whichever method you want. But I do want to see that you know how to use each one. So on the assignment tonight, make sure you're using the methods that the directions ask for. So looking at the first equation in this system, we need to solve it for y. So to do that, I can subtract 3x from each side first. So then 2y is equal to negative 3x minus 2. That is correct. Now, I know I always say, and I will continue to say, if you're graphing especially, leave your slope as a fraction. Because we're going to be making a table, it might be easier when you're calculating if you have a decimal. So if the fraction were to be a terminating decimal, if you write it as a decimal, that's fine. So I could leave this as negative 3 over 2 because I'm not graphing it. If I changed it to negative 1.5, that might be easier to calculate. And then minus 1. So that's one equation. And then the second equation, I also want to solve for y, so I need to add 4x on each side first. So 5y will equal 4x minus 28. And then divide by 5. So y will equal, and actually both of these fractions as well, dividing by 5 will become a terminating decimal if you change it to a decimal. So 4/5 is 0.8 if you would rather write it as a decimal for this problem. Minus 28/5 is 5.6. So then when I make the table, I'm actually going to have 3 columns in the table. The first column will be the x values I'm substituting in, and I'm substituting it into 2 different equations, so I need 2 different columns for my 2 different y values. So I'm going to write the first equation in that second column, and I'm just writing the whole equation rather than just y, since I'm going to have 2 different y values, and the second equation in the last column. And as I suggested in that table, starting with 0 is easiest. 0 is the easiest value to plug in. Even if you can see that it's not going to be the solution, the y values won't be the same, still plug it in and I'll explain why. So when I substitute 0 into my first equation, the term with x will just become 0 because I'm multiplying by 0, so I'll just have -1. And the second equation, I'll just have -5.6. So these are not the same values, meaning my solution isn't here. So now I'm going to try a different x value. I'm just going to go up to +1. So now if I substitute in +1, this is where you're not expected to just do everything in your head. Calculator might be handy. But -1.5 times 1 is -1.5, minus 1 is -2.5. And then 0.8 times 1 is 0.8, minus 5.6 is -4.8. Yeah. Okay, so my solution isn't there either. These y values are not the same. But now what you should look at is the y values from when you substituted in 0 versus the y values from when you substituted in 1. Did they get farther apart or are they closer together? They're closer together. If you're not sure just by looking at it, you're looking at it now and thinking, I don't see why they're closer together. You could find the difference between the y values by taking the larger one and subtracting the smaller one. So if I took -1 and I subtract -5.6, this is a difference of 4.6. So they're 4.6 units apart versus -2.5 minus -4.8. That's a difference of 2.3. So they are closer together. So since they're closer together, that means now if I substitute in, if I continue going up with my x values, if I substitute in 2, those y values should even be closer together or even maybe the same, because ultimately you want them to be the same number. So if I substitute in 2, has anybody substituted 2 in already? Ethan, what did you get? -4 for both. Okay, and that's what you want. You want the y values to be the same. So once you reach this point, that means the ordered pair that satisfies both equations, the ordered pair that is the solution, is the ordered pair when the x-coordinate is 2 and the y-coordinate is -4. And you should write your answer as an ordered pair. So don't just circle this line in your table. I highlighted it to make a point, but that's not how you write the solution. The solution is an ordered pair. Questions on example 1? Okay, so example 2, even though it's the same method, I like to include examples that just work out a little bit differently. So example 2 will be a little different. I need to start out the same way, solve both equations for y. So for the first equation, I would have to subtract 4x from each side first. So 3y equals -4x minus 17. and then divide everything by 3. Now, when you divide by 3, you get repeating decimals, meaning you have to leave the fractions as fractions. Because if I change the fractions to decimal approximations, that means when I make my table, all of the values I get for that equation are going to be approximations. They won't be exact. So you want to keep them exact, otherwise you're not going to find your solution. So I have y equals negative 4/3 x minus 17/3. If you put 17/3 as minus 5 2/3, that's okay if you had a mixed number. Just don't put 5.6 repeating. So that's one equation. For the second equation, I have to add 7x to both sides first. Make sure the minus sign that's in front of the 2y stays with it, so it's negative 2y equals 7x plus 20. And then divide each side by negative 2. So y equals, now dividing by 2 will give you a terminating decimal, either that or an integer. So 7 divided by negative 2, I can write that as negative 3.5x. And then 20 divided by negative 2 would become a minus 10. So I'm going to set up my table, x column, y equals negative 4/3 x minus 17/3 in the second column, y equals negative 3.5x minus 10 in the third. And I'll start out the same way, substitute in 0. Again, even if you know it's not going to work, it's good to know to compare if your y values are going to be getting closer together or farther apart. So if I substitute in 0, then my y value for the first one will be the negative 17/3, which is negative 5 2/3. Perhaps looking at the mixed number there. Or even if you wrote this as a decimal, just to have an idea of how far it is from the other number, that would be okay. And then for the second equation, I would have just negative 10. Okay, not the same, so I have to keep going. So if I substitute in 1, then I would have negative 4/3 times 1. So negative 4/3 minus 17/3. That would be negative 21/3, which negative 21 divided by 3 is negative 7. And then for the second equation, negative 3.5 times 1, so negative 3.5 minus 10 would be negative 13.5. So what do you think? Closer together or farther apart? Okay, if you're not sure, I heard John say farther apart, but there's silence everywhere else. So if you're not sure, subtract them. So if I take negative 5 2/3, I could even round that, say it's negative 5.7, because it's negative 5.6 repeating. So if I take negative 5.7 and I subtract negative 10, that is a difference of 4.3, so it'd be 4 1/3. Because I had rounded to the decimal. And then negative 7 minus negative 13.5, this is a difference of 6.5. My difference got larger. So if I substitute in positive 2, my y values are going to be even farther apart. I'm going the opposite direction I want to be going. Yeah, so I should go the other direction for x and substitute negative 1 in. Do you have the y values?
No, I have a question.
Oh, okay.
So for the first one, you put negative 17 over 3 equals negative 5 2/3.
Yep.
What if I just wrote negative 5.6?
That's fine.
Oh,
Yeah,
for this
number, yeah, that's fine. I figured this would be easier to look at to compare how far away the numbers were if you didn't have the improper fraction. That's why I wrote it this way. But if you had negative 5.6 repeating, that's fine. Did anybody substitute in negative 1 already? What did you get? Okay, so not the same. And this, if you had, this would be negative 4 1/3. So they are closer together, for sure. So then I should substitute in negative 2 next. Did you substitute negative 2 in as well? Negative 3 for both. What did you say, Jen? If it's negative 13/3, it'd be negative 4 1/3. It'd be negative 4.3 repeating. Okay, so here's where the y values are the same, meaning our solution is the ordered pair negative 2, negative 3. And again, make sure you're writing it as an ordered pair. Okay, so just using a table, kind of an extended table with two y values, is a fine way to solve a system of equations. And if it says solve by using a table, this is what it means. Any questions before we move on? Okay, then solving by graphing. So this you're probably more familiar with. This is for sure in Algebra 1, because this is the big idea of why the solution is an ordered pair. You want to write each equation in slope-intercept form so you can graph it. Then graph each equation on the same coordinate plane. And where the two lines intersect will be the solution. So looking at the first equation, we have to get the y by itself, put it into slope-intercept form so we can graph it. So we'll subtract 2x from each side. Make sure the negative stays in front of the y. Negative y is equal to negative 2x minus 1. Yep. Divide or multiply everything by negative 1. So y is equal to positive 2x plus 1. And before I solve the other equation, I'm just going to graph this one right away. So you can graph this by making a table. You can also just graph it using the slope-intercept form. So based on this equation, where would my first point be on my graph? Positive 1, where though? Which axis? On the y-axis, yes. So y-intercept is your b value, that's positive 1. Make sure it goes on the y-axis, not on the x. The slope is positive 2, which is 2 over 1. So I can go either up 2 and right 1 or down 2 and left 1. But my line should be increasing. And you only need, you really only need 2 points to graph a line. I did not put the rulers out for you to use today. So typically what I do, I mean, if you have your own straight edge, go ahead, use it. I will usually plot more points than is necessary for my first line so that when I graph my second one, I can more easily see where they intersect. So this would be my first line there. Make sure also, I see too many students do this where they just plot the points and they don't actually draw the line in. If you just plot points, you did not graph a line. So make sure you're actually drawing the line. And then for the second equation, solving for y, you have to subtract 5x first. So 2y equals negative 5x minus 16. Divide each side by 2. Y will equal, leave this as a fraction now for your slope because you're graphing, so negative 5 over 2x, and then minus 8. So the y-intercept is negative 8. And then the slope is negative 5 over 2. So we should be going either down 5, right 2, or up 5 into the left. And I can't go down without being off the grid. So I'll go up 5, left 2. And I can already see where the two lines intersect. I'll just make another point just to draw my line a little bit straighter here. So where the two lines intersect is the solution. That is what the solution to a system represents graphically. What ordered pair do they intersect at? What ordered pair is this?
-2, -3.
Thank you. Questions on solving it by graphing? The graphing part, getting the solution. How to find it. So you understand the B as your first point, and then this is your M. So right, or your slope is your rise over your run. So if you write your slope as a fraction, the top number, and usually if it's negative, I'll include the negative with the top, but the rise is how far you move up or down. So if the top number is positive, you would move up. If it's negative, you would move down. And then the bottom number is your run, and that's how far you move left or right. So if it's positive, you move to the right, negative, you move to the left. So like -5/2, I would typically go down 5 and then right 2. But because I would be off the graph, I can also do the exact opposite and go up 5 and then left 2. Does that make sense? Okay. That's a good review for everybody. Graphing with slope. Okay, then what I would like you to just discuss quickly, 30 seconds. I didn't mention this, but what I have also seen students do is they're very careless with how they draw their lines. They just kind of swipe their pencil through it and there's a line. And then they end up getting the wrong solution because their lines aren't completely straight. Usually graphing is not an exact way to get a solution, it's more of an estimate. So how could you make sure that this solution is actually correct? So I want you to discuss with each other for 15, 30 seconds. And then I'll just pick a group and ask what you talked about. Make sure that you're still.
Also,
Wait, give me one.
Did you finish the notes? That's why they asked for it, because they did all the examples already.
Alright, then I'll finish the note.
All right, so how would you check this solution? Well, actually, I've heard from Ethan quite a bit, so. But I want to make sure more than just Ethan knows what's going on.
What?
Well, John, you had your hand up. How would you check it?
So you plug in your equations where they intersect for both equations, if they equal the same thing, right?
Yep. Make sure it's plugged into both. Which equations would you plug it into? The original
No,
or?
not the original, the final. You can plug it into either or.
Well, it doesn't matter, but what if you rewrote them wrong?
Well, then you rewrote them. Oh, plug it into the original, so you might do it.
Yes, so here's the thing. It doesn't really matter where they're plugged in, except your answer is going to be wrong if you rewrote your equations wrong. So really, to be 100% sure it's right, you should substitute the ordered pair into the original equations, because then if it's wrong, either your graph is wrong or maybe your equations themselves are wrong. So if you want to make a note to yourself, I'm never going to ask you to show me your check, but I want you to know how to do it, because on a quiz or test, you could check all of these answers before you turn it in and know if you have them right or not. And the idea or the hope would be if it's wrong that you would try to figure out how to fix it before you turn it in. So to check, you would substitute the ordered pair into the original equations. So you kind of always defer back to what you were given in case anything went wrong in any step leading up to your answer. That would be the way to check and make sure that your answer is correct. And it has to be substituted back into both. Okay, so understanding how to check, that's important. So are we good if I flip this over? Okay. The last part of this is a classifying system. So a system can have 3 different types of solutions, I guess I'll say. Your system could have exactly one solution. All of the examples we've done so far have had one solution, and that's if your 2 lines, when they're graphed, intersect at one point. Your lines or your system could also have infinitely many solutions, and that's if the 2 equations you have represent the same exact line. So because there's infinitely many points on a line, if the 2 lines are the same, they intersect at every single point on that line, which, like I said, there's infinitely many. And then it is also possible to have no solution. If your lines are parallel, they will never intersect. And if they don't intersect, there's no solution. So to classify a system, this is where you don't say what the answer is, but you say whether it's consistent or inconsistent, and then independent or dependent. So consistent, because I know these are written up above, so you can see for one solution, for example, it's consistent and independent. But here's why. Consistent means it has at least one solution. Inconsistent means it has no solutions. If it has a solution, then you want to specify, does it have exactly one or does it have infinitely many? So independent means it has exactly one. Dependent means it has infinitely many solutions or an infinite number. Make sure, I'm just going to say this now because I always have students do this because they don't actually want to write out the word infinitely. You may not put infinity as your answer for this. If you do that, I will not accept that answer and you will lose points. Because these mean 2 different things. There's a difference between infinitely many solutions and then answering and saying my solution is infinity. Okay, your solution is not infinity. You have infinitely many solutions, but infinity isn't even a number. That's not your solution. So you may not just put the infinity symbol. Write out the word. It takes a couple seconds. Okay, so in example 4, this is just one additional example. But if you see in the directions to graph and then describe the system using these terms, then make sure that if you give the answer, it's fine, but you also have to classify it. So say consistent or inconsistent, independent, dependent. So in graphing this, I know some of you might have worked ahead. We need to solve the first equation for y. If you have worked ahead, just make sure that you're checking that you actually have it right. So we would need to add 2x to each side first. So 5y equals 2x plus 10. Divide each side by 5. Y will equal 2/5. Leave that as a fraction. X plus 10 divided by 5 is 2. I'll graph this before I solve the other equation. My y-intercept, b, is positive 2. So at 2 on the y-axis, I put a point. My slope is 2 over 5, and it's positive. So I would go up 2 and write 5 from my y-intercept. And again, I typically plot more points than may be necessary. In case the lines intersect, I want to see where they're going to intersect. And then for the second equation, solving for y, I'd need to subtract 4x from each side first. Make sure the negative stays in front of the 10, so negative 10y equals negative 4x minus 20. Divide each side by negative 10, and y will equal, a negative divided by a negative will be positive, but 4/10 will simplify to 2/5 x, and then negative 20 divided by negative 10 is positive 2. What do you notice?
Huh?
What do you notice?
That they're
Well, yeah, they're the same line. So if I graphed this, it would be right on top of the one I already graphed. So it is consistent and dependent because how many solutions does it have? An infinite number, yes. So there's infinitely many solutions. So if you were asked for the solution, this is what you would answer. If you're asked to classify it, this is your answer, the consistent and dependent. So make sure, though, if you were to solve these both for y before you graphed, and you could see they were the same, if the directions say to graph the system, you still need to graph it. So just make sure you're doing that. And then I'm going to pass out the assignment, but I want you, talk about it in your groups, please. You can write it down. I'll just make sure when I'm done passing out the assignment that we understand what the answer should be. So without graphing, how would you be able to tell if a system was inconsistent? And make sure in your explanation that you point out what inconsistent actually means. So without graphing, how could you tell if a system was inconsistent, is the question.
I don't even do it. I appreciate it. I appreciate it.
Did everybody get one? Okay. How could you tell if a system was inconsistent? Andrew? If it doesn't have the same slope? What does inconsistent mean? Does have the same slope, yes. Because inconsistent means what? How many solutions? If it's inconsistent. 0 solutions. What kind of lines will have no solution? Parallel. Parallel lines have the same slope. Now, I would argue, though, these two equations in example 4 had the same slope. Are they parallel lines? Yes, thank you. Okay, so I realize you're starting on your assignment, but tune in up here. This is important for your understanding. If an equation, if a system is consistent and dependent, these equations still have the same slope, but they're the same line because their y-intercepts are also the same. So here's how you could answer this question. You don't have to change what you have. But in this explanation, it would be good if I said what inconsistent actually meant. So I'm going to say, since inconsistent means no solution, the lines must be parallel, meaning their slopes are the same, but their y-intercepts are different. So in case if you can't read something I wrote and you want to just double check what you have, you don't have to word it the same. Like I said, obviously if you were just writing something, you wouldn't say it exactly how I would. But I would look to see, did you say that inconsistent meant no solution? The lines would need to be parallel. And then in your explanation too, make sure rather than saying their m's are the same, say their slopes are the same. Use that vocabulary and say they don't have different b's, but they have different y-intercepts to say what that means.